Hello. Today I will talk about a topic within cosmic inflation and notably about the production of primordial black holes and how spectator fields may foster this production. This is based on recent work with my collaborators Scalar, Zach Ireland, Dave Kaiser, Evan McDonough, and Kyle Wittmeier. And before we start, let me just give you some context of what we will be looking at. This is cosmic inflation, which is a very brief epoch of exponential expansion of space that took place in the very early universe, before the cosmic microwave background was formed, before the development of stars and galaxies, and long before the accelerated expansion of the universe driven by dark energy that we can observe today, and that I am sure we'll have heard very interesting discussions about during this conference. So, what will I discuss today? Let me give you a little story. First, I will introduce cosmic inflation, and I will define what primordial black holes are. And I will also introduce a third piece of the puzzle, which is this idea of spectator fields. Now, we shall see how spectator fields may hinder the production of primordial black holes during inflation, but we will then see that this is not necessarily the case. Due to a new mechanism that we have identified, spectator fields may not only not hinder primordial black holes, but may foster their production. And now let's just jump straight into things. So we said inflation is this early brief phase of exponential expansion of space. And this was introduced in the 1980s to solve some outstanding problems of standard Big Bang cosmology, notably what's called the horizon problem, which basically is the question of when we look at the cosmic microwave background, the earliest light we can observe at opposite sides of the sky, we observe the same temperature to 1 part in 10 to the minus 5. However, those patches, according to standard Big Bang cosmology, would not have been in causal contact. So how is it possible that they had such a similar temperature? Through cosmic inflation, through this idea of very quick expansion, those patches would have been in causal contact earlier and would have therefore been able to thermalize and get to this very similar temperature. Now, inflation has been extremely well tested against the real data, notably the CMB and baryonic acoustic oscillations, but also through the observation of large-scale structure. And inflation allows for very interesting phenomena to take place. Notably, inflation gives us a mechanism for the production of large-scale structure and for the production of the particles of the standard model. But it also gives us possible candidates for dark matter. So let me just give you a couple more details about inflation and its physics. In the simplest realization, inflation is driven, this exponential expansion is driven by a single scalar field, phi, the inflaton, that lives in a certain potential. And here by scalar field, I mean a spin zero particle, such as the Higgs. Now, if this is the case, like we can see in this animation, the field would roll down its potential. And if it rolls slowly, what we call slow roll, this can cause the expansion of space. So the rolling of the field through its potential can cause the space itself to expand very fast. However, because of quantum mechanics, because of Heisenberg's uncertainty principle, we know that there also have to be quantum fluctuations of energy throughout the trajectory of this inflaton field. And what is interesting is that as these fluctuations go, they seed the production of the CMB and of large-scale structures such as the galaxies we observe today. Now, after inflation ends, you might have noticed that my field is wiggling again around its minimum. It's not just a bug of my animation, but this is because around its minimum, the inflaton transfers its energy to the fields and the particles of the standard model. So we have a way to produce the particles we know and love. And all of this is described by an action that takes this form where we have a kinetic term and a potential term. Now, to test inflation, we have to look at certain observables, and the main one of those is what's called the curvature power spectrum of inflation, which is the two-point function of these quantum fluctuations, which are therefore very important in the study of inflation and in testing it's possible whether it took place or not. And the power spectrum leaves an imprint on the cosmic microwave background, which, as you probably all know, is the richest source of data for cosmology. And in particular here, K is a three-dimensional wave number, which gets reflected into the multiple moment L, which is the Fourier decomposition on the surface of a sphere. Now, the hallmark observable of inflation is its scale dependence, the scale dependence of the curvature power spectrum, which we know to 8 sigma. So we're very certain that the power spectrum is scale dependent. And to test this, and observe this, we look at the amplitude and the slope of the power spectrum. Now, let me switch gears and briefly talk about primordial black holes. What are they? As like their stellar cousins, they form through gravitational collapse. However, instead of being the gravitational collapse of stars, it's the early gravitational collapse of overdensities. That is, regions of space where the density is larger than its surroundings, taking place in the very early universe. And these overdensities are sourced by the very same fluctuations, the quantum fluctuations that we saw happen during inflation. Now, primordial black holes are also a candidate for dark matter, an interesting one at that, because they don't require any additional physics. You only need GR and the particles of the standard model. And they could also be the seeds for the supermassive black holes that we observe at the center of galaxies nowadays. Now, for this to take place, we need, for these inflationary fluctuations to source large enough overdensities, we need an enhancement of the curvature power spectrum of inflation to above a threshold of around 10 to the minus 3. Consider that at CMB scales, the power spectrum has a value of 2 × 10 to the minus 9. So how can this happen? And one way to do this is through what's called ultra-slow roll. So the background dynamics of inflation are governed by these two equations, the equation of motion on the left and the Friedmann equation on the right, where h here is the Hubble parameter that describes the expansion of space. Now, we can define what's called the slow roll parameter epsilon, which is really proportional to the square of the velocity of the inflaton. And when epsilon, which tells us about how fast or slowly the inflaton is rolling down its potential, if epsilon is very tiny, we call this ultra-slow roll. And when ultra-slow roll takes place, we accumulate fluctuations, we accumulate curvature perturbations that therefore cause this enhancement of the curvature power spectrum. For this to happen, what we usually consider is very tiny bumps in the inflationary power spectrum, sorry, not power spectrum, but potential. So in this potential here that has this form, we can see that there is a tiny bump. During that bump, for lack of a better word, this is literally a Gaussian bump overimposed over what's called the KKLT potential. The field slows down because of the shape of the potential, slows down, producing a phase of ultra-slow roll, increasing or accumulating all these curvature perturbations and enhancing the power spectrum, and then continues its merry way along its standard slow evolution. Now, in come spectator fields, and let me start by asking this question: is the universe simple? So we all know, and some of us may have this model, this mug by CERN, on which is printed the Lagrangian of the standard model of particle physics. But if we were to expand each of those terms, this mug would look something more like this, which, let's just say, is a bit more complicated or complex. And we also know that there are multiple scalar fields present in the universe. The Higgs in the standard model is a complex doublet. That means it's 4 scalar fields. And even in its original formulation, there's a complex scalar field, such as the one shown here, which includes 2 scalar fields. Now, if we go beyond the standard model, we can have multiple Higgs, and in general, very high numbers of scalar fields. For example, in string theory, flux compactification, we can have hundreds of axions, which are scalar fields, and even GAN unified theories, which are very popular when inflation first started being developed, predict multiple scalar fields. So no one field has any reason to be special as the inflaton. And so by spectator, we mean one of these additional scalar fields. And in particular, we mean an additional scalar field that is not coupled to the inflaton. So the action principle will look something like this, where we now have this extra kinetic term due to the spectator field that I will call chi moving onwards. And also the potential will take two terms. We'll have a term depending on the inflaton, and this will be the inflaton potential that gives us primordial black holes, and a second term due to the spectator field itself. Now, because they are not coupled kinetically, and because we don't consider non-minimal couplings to gravity, the Slowell parameter that we saw earlier is sum separable. It will have two components due to the inflaton and spectator parts. When we plot this, what happens is that during what would be the USR phase, the ultra-slow phase in single field inflation, so when the epsilon phi becomes very tiny in what I call here phase 2, the spectator field sets a bound on how small epsilon total in black can be. And basically what happens here, and again, this is the same potential I basically showed earlier, where for the spectator, we just consider quadratic potential. What happens here is that the total epsilon can never reach these very tiny values necessary for ultra-slow to take place. So you may wonder, what happens? Do we kill primordial black holes? Because we're skipping inflation, we're skipping not inflation at all, but the ultra-slow evolution. And indeed, naively, we might see that the power spectrum gets, when we don't consider USR, gets cut to values far below the 10 to the minus 3 threshold necessary for producing primordial black holes. However, hope is not lost. There is a new mechanism that is caused by the fact that we now have two fields. In particular, in the presence of two fields, we have a field space, a two-dimensional field space, and because of the trajectory of the fields, we can have turns in field space. And these are described by this ternate omega. Now, during phase 2, which, let me remind you, is the phase during which single field evolution would have a phase of USR, but in the presence of the spectator, we skip that. During that phase, the system turns from moving along the phi direction, the inflaton direction, to the chi direction, and then turns back to moving along the inflaton direction. Now, in the case where we have multiple fields, we also know that we will have two sets of perturbations, these inflationary fluctuations that we mentioned earlier, both along the trajectory of the fields, which are called curvature, and perpendicularly to this trajectory. And what we know is that these perturbations are governed by two equations, which I'm showing here. And if we look at the second one first, what this tells us is that isocurvature can go when this mu(s)² term is negative, which is what we call a tachyonic phase, because this is a mass term. It's the mu(s)² is the effective isocurvature mass. So when mu(s)² is negative, S can go. The first equation tells us that there can also be a transfer of power from the isocurvature to the curvature modes in the presence of a term when omega is non-zero. And indeed, this is what we observe. So when we plot the evolution of the isocurvature mass, we can see that during phase 2, when we would have had USR, but we skip it, we have tachyonic instability. And during those times, indeed, the isocurvature mode goes very quickly. And then at the end of phase 2, when we have a turning back towards the inflationary trajectory, the inflaton direction, we have a transfer of power from the isocurvature to the curvature mode. Now, this means that not only do spectator fields not kill primordial black holes, but they might even foster their production. They might enhance the power spectrum even further. Now, as a bonus, let me quickly mention fine-tuning. So models of inflation that produce primordial black holes are linked with the problem of fine-tuning. That is, very tiny changes in their parameters can change their observables significantly. And this is shown in the same model we were looking at earlier. This model depends on a parameter phi d. And if I change phi d by a very tiny fractional value, 10 to the minus 4, the peak of the power spectrum quickly drops to far below the threshold for primordial black hole production. So these models are exponentially sensitive to very small changes in their parameters. However, when we include a spectator field, and here this dashed line has the same model parameters as the original black line, but also has a spectator field. When we have the situation, the same change in the PBH parameters, in this phi d parameter, can be easily compensated by order 1 changes in the spectator field parameters. So the model is much more resilient to these small changes, and this problem of fine-tuning is somewhat alleviated. And furthermore, this we know because of our theory that we would expect additional fields to be present. So let me quickly recap everything I've said. So we know that in single field inflation, there can be models that produce primordial black holes through this mechanism called Ulta's low roll. And this, however, requires significant fine-tuning of their parameters. On the other side, we know that spectator fields should be present, or we expect them to be present in your universe. So what happens when we include spectator fields in our inflationary models? And naively, what we would expect is that because they stop USR from taking place, we would expect them to kill the production of primordial black holes. However, as they source a new mechanism, these turns in field space, this does not happen. And in fact, we can enhance the curvature power spectrum. And as we just mentioned, this can also alleviate the problem of fine-tuning or make the model more resilient to these tiny changes. And on this note, thank you very much for your attention. And I'm really curious to hear and read any questions you may have and to discuss these further soon. Thank you very much and goodbye.